everyone, this is Andrianna Mancil, and today I'll be discussing Physics 1, Lab 1, Constant Velocity. And today we'll be going over some important experimental details, fundamental physics principles involved in this experiment, and the two models, the observational and the computational model, compared and contrasted later in this video. First, let us go over some important experimental information. In my experiment, I chose to analyze a basketball rolling across the court at a constant speed in a singular direction. I created two models in which I compared the position versus time graph in meters versus seconds. The observational model is created using a video analyzed in Tracker, and the computational model is created using Python coding language in GlowScript. An overview of the final results is that both models created similar plots on the position versus time graph. Although some differences in the slopes and graphs point towards possible error in observation, model development, and other sources, but we will discuss those later in the presentation. As the ball moved in constant velocity in the same direction, the graph that is observed in both models displays a positive linear-like slope. But again, we will discuss further differences later in detail. Now let us go over some of the fundamental physics principles involved in this experiment, like Newton's first law, Newton's second law, and the momentum principle. We know from Newton's first law that an object moving in the same direction at a constant speed will continue to move in a constant direction and speed until a force acts on that object. In addition, an object at rest will continue to stay at rest until a force acts on that object as well. From Newton's second law, we know that force is equal to mass times acceleration, and that is also equal to mass times the change in velocity over the change in time. We also know that the final velocity is equal to the initial velocity plus the total net force divided by mass times the change in time. If the total net force is zero, we are able to indicate that the final velocity is equal to the initial velocity, thus showing that it is moving at a constant velocity. The mass of the basketball was noted to be 0.9072 kilograms, and the diameter of the basketball was 0.234 meters. Next, I took a video of rolling the basketball on a flat outdoor court with little distractions in the background and a good lighting. Then I opened and analyzed the basketball video in the app Tracker. I was able to set a calibration stick of a known dimension in the video, establish axes, track the center of mass in a specified time frame, and save the position and time in a separate spreadsheet. Here's what we learned from the experimental observation. As time passed, the graph of the position of the basketball displays a mostly linear slope. The basketball appears to move at a constant velocity. But, towards the end of the observational time frame, the position of the basketball versus the time passed displays a curve beginning in the graph, indicating that there may be additional forces and no or a less constant velocity. Now that we've discussed the observational model, let us move on to the computational model. Using the given Lab 1 starter code, I changed, added, or edited lines of code to attempt to correctly create a working position versus time model. Below are some of the lines of code that were updated. Line 32 is updated to correctly represent the mass, and line 36 is updated to correctly represent the change in velocity using the initial tracker values. Next, line 40 is updated to correctly represent the size of each time step, and in line 49, the while loop is updated to correlate to our time values in Tracker. Next, the net force is updated to equal 0 to include that the net force acting on the object is 0. And finally, line 58 and 60 are updated to include the proper equation and correlating syntax to Newton's second law. Here, let us take a look at our starter code versus the updated lab code. When the program runs, this is what it presents on the right. Here, a constant velocity with an increasing linear slope is observed. Finally, let us discuss the results of the graph of the observational model and the computational model, and what to take away from this. The graph from the observed data and the graph from the predicted computational data are close to one another, but still exhibit some strong discrepancies. They have similar plotted positions and similar slope, but they do have differences in velocity. Computational model continues to increase linearly, while it increases more quickly than the observed. But the observed model transitions from a linear to a more curved graph with a lower, no longer constant velocity, and it seems to increase less quickly than the computational model. Let's go over some of the major differences. Both are similar in position versus time graphs in the beginning, but as time passed, there are more differences in the two graphed models. In the observed model, it is possible that it endures additional forces such as contact or friction with the below surfaces and imperfections in the object shape or even more additional factors. In the computational model, it ignores the other possible sources of force such as friction, drag, gravity, and more, and it follows Newton's second law. In all, due to Newton's second law, if the basketball experienced a net force of zero, it would have continued to move in a constant direction at a constant speed, like seen in the constant velocity of the computational model. Because of this additional forces, the two models differ. Finally, in the future, I would record on a smoother contact surface, utilize smaller time intervals, and try to choose a more accurate center in the app tracker to produce more accurate results. If I were to change my axis direction, the sign of my slope would also change accordingly. And finally, it is not feasible to calculate the exact amount of force on an object that are added to give zero net forces.